The notion of limits and continuity are complicated concepts. There are epsilons and deltas dangling everywhere. You have to choose delta appropriately so that something happens, so on and so forth. We are now going to ease our burden by introducing a convenient language for speaking about limits. We will not use this language extensively because this is, after all, a first course where you have to write everything properly and rigorously. But nevertheless, and several instances in this course, it will be very useful to have this language at our disposal. So, just like language for limits, we talked about quantities getting close to each other as the number n became arbitrarily large, right? So we are going to introduce similar notions for limits. So definition. Let S be a set and let X be a limit point of the set S. Let P be a property defined, or rather let P of X be a property defined on S. We say P holds for X arbitrarily close or sufficiently close so best to call this limit point something else so that there is no confusion. Let's say C be a limit point, close or sufficiently close to C if P of X is true whenever mod X minus C is less than delta and X is in S, whenever there is some delta greater than 0 such that 0 less than mod X minus C less than delta and X is coming from S. So let's revisit this. You have a set S and you are choosing a limit point C of this set S. You have a property P of X defined on S. We say P holds for X arbitrarily close or sufficiently close to C if P of X is true whenever there is some delta greater than 0 such that 0 less than mod X minus C less than delta and X is less than S. So to be 100% precise, if you don't mind, let me just reorder this way I'm writing so that things become clearer. If for some delta greater than 0, P of X is true whenever 0 less than mod X minus C less than delta and X is in C. So what this is saying is you can make the property P true if you can find some delta such that P of X is true whenever X is sufficiently close to C and X is coming from C. We don't allow X equal to C simply because this C may not even be in this set. And the way we write this is analogous to way we define limit. It will be useful there. Okay. Now, next is definition. Another definition. Let S be a set. And let C be a limit point. Again, limit point of the set S. Let A of X be some algebraic expression involving x coming from S. Okay, we say a of x can be made arbitrarily small as x approaches C. Now this should be very familiar. If for each epsilon greater than 0, we can find delta greater than 0 such that mod a of x is less than epsilon whenever mod x minus c is less than delta. Okay, so this just giving another meaning for the term limit. Okay, this is just saying that limit as x goes to c of a of x goes to 0. We are just calling it can be made arbitrarily small. Okay, now why is this first and second definition useful? Well, remark we can combine both these. We can combine both to talk about limits. Okay, how do we do this? Well, we can rephrase limit x going to c of f of x equal to L as saying mod f of x minus L can be made arbitrarily small for x sufficiently close to C. Okay, this is sort of combining the meanings of both the preceding definitions. Instead of saying limit x going to c f of x equal to L just means that given any epsilon greater than 0, there's a delta greater than 0, blah blah blah. You can just say mod f of x minus L can be made arbitrarily small for x sufficiently close to c. This is a concise statement, but nevertheless with the preceding definitions it's a very precise statement. And not only that, this is a nice way of thinking about limits. You make x sufficiently close to c, mod f of x minus L can be made arbitrarily small. We have translated our intuition into rigorous mathematics via epsilon delta. Now that we have processed, understood and made it part of our circulatory system, it's best to now go back and try to use words that have more expressive meanings like arbitrarily small and sufficiently close. But you should be very careful when you speak of this language, because when you use such language, there is always the tendency to delude yourself into thinking that you have understood what is going on, or worse, write proofs that seems to make perfect sense, but when you translate to rigorous mathematics, the proof breaks down. So in this course, I will minimize using such language, but the literature uses such language all the time. Okay, uses such language all the time, so it's best to be familiar with what this means. Okay, so this is a convenient language for talking about limits. We can also talk about infinite limits. That will be the content of another module, where we'll be talking about arbitrarily large instead of arbitrarily small. Okay, this is a course on real analysis and you have just watched the module on a language for limits.